Marty, thanks for joining us. Hey, everybody, welcome to the Magnitude 10 this month. We have Marty from Fife on. He will tell us everything we need to know about FRP. I don't know if you guys know all the history of FRP. I actually don't know all of it. I was introduced to it right after the Northridge earthquake, where I think we did some of the very first fiber wrapping in Centinela Hospital after the earthquake there. We strengthened some shear walls and wrapped some columns and did a whole bunch of stuff because it didn't really have room for shotcrete. and Ed was very active in the business.
Minimum real estate, yeah.
Ed was very one of the world's greatest innovators, I always thought. And Ed Fife has been a huge fan of Miyamoto Relief and been very helpful. So
good.
Yeah, Ed's no longer involved, I think, in the company, correct? But he's a one man.
Correct. Yes.
Yeah.
But one of the individuals that was with Ed at the beginning, our director of engineering, Scott Arnold, is still with the company, and he's seen a lot, experience with a variety of applications over the years, and a great technical resource.
Yeah. Scott's always the first person I call if I ever have a question that I know he can answer.
Yeah. There's a good chance he has seen a similar or pretty close application to date.
Yeah. So with that, have at it, Marty. Thank you.
Thank you, Jeff. Well, good afternoon, everyone. My name is Marty. I'm my title is Business Development Manager for Fife, based in Northern California. And I'm actually, I'm really happy to be able to be with the company. And it's been, I've recently joined the company, actually. It's been about 5 months in this role. And it's something that I've sort of, FRP is something I've kind of known about for a while, and had a respect for it from a high performance, low impact product for retrofit solution. And an opening came up. The gentleman that was in my role, Jose Duran in Northern California, went back to school to get his master's degree, and I was serving as previous to this, I was serving for almost 10 years with DeWalt, taking care of anchors for concrete. So field engineer for DeWalt on the anchor side, anchors for concrete, anchors for masonry. I've been presented to the Northern California Miyamoto offices in Sacramento, San Francisco, San Jose. But really excited to have the opportunity to join Fife. It's a great company, some good folks on hand from the engineering side, and also my colleagues from the business development side. And so just a quick introduction here. If you're not too familiar with Fife, we are actually a manufacturer of fiber reinforced polymers. So we supply the product, the epoxy that goes along with it, that saturates the fabric and creates the polymer, a variety of different FRP materials, including anchors, which we'll talk about later. But we're a supplier. We also provide support on the engineering side. But the model is that the actual install takes place by a team of what we call applicators, or certified, that are certified to work with Fife products. So we train these quote unquote, they're like specialty contractors that are trained in installing FRP, and they generally submit or work as a sub to the GC. So we have a team across the country. In Northern California, I have a group of a handful, 3, 4, 5 certified applicators that we work with, that we partner with, that we pursue projects on, and down in Southern California as well, and across the country. So that's sort of our business model, and it works pretty well. We train them, and we have a pretty good assurance that they're knowledgeable and capable of installing correctly, and we have a pretty good working relationship with them, so we're in regular contact. That's a little bit of the business model. And some of the other things from the Fife side, what we offer as a company that, what we like to think are great assets is the engineering backup. So we have a team, I mentioned Scott Arnold, he's our director of engineering, and we have a team of design engineers. And what we do from the engineering side is offer support to consultants, and at no cost, either on a feasibility basis, if you're got a candidate, a retrofit candidate, and you want to take a closer look at FRP and maybe you want to consider it as an option, we will take a look at what you have there in the way of existing conditions, performance criteria you're looking to establish, and give you some feedback. If it does look like you want to move forward, we will help support you there, develop the project, again, at no cost on the front end while you are developing construction documents. So help you develop a spec, general notes, details, provide you feedback on, performance criteria, and what we can do. And then from there, once it does, decide to move forward and issue for construction and bidding to the GC, as I mentioned earlier, we'll work with our local applicators, provide them with a FRP specific design and the required materials involved and the whole package for them to take and submit their bids to the GC. And that's sort of how it works, but we are available to help, and on any of your projects. That's sort of what we do, and we have pretty good relationships with a good number of consultants out there with that service. Manufacturing, we've been involved in the industry as a company for over 30 years, so dating back to the late 80s, early 90s. Ed Fife started the company and pioneered the use and consideration of fiber reinforced polymer materials. So we've been involved with hundreds of projects, different applications, buildings, bridges, for seismic, for waterfront, industrial facilities, and so we've seen quite a bit there and have a good track record. And then lastly, training. So as I mentioned, we have applicators that we work with that we train and we certify. We have a field manager that almost has as much experience as Scott. He's been with the company over 20 years. He goes out and will either train applicators and certify applicators on site at the job site, at their facility. He's also lately been doing virtual training. And so we have, and then again, he's seen a lot, and he's really good at getting these contractors up to speed, covering everything. He's really thorough. And then additionally, field support and on-site QC. So once a project is up and running, myself or the field manager, local staff and personnel, as any issues that might come up or questions from the contractor, are available to go on site, inspect, generate reports as need be, or provide input on maybe certain application conditions. So the materials that come into play, the fabric, there's two main types. So for FRP, and that would be glass and carbon fiber. On the glass side, the materials and the product line that Fife provides is known as TIFO. And TIFO, from what Scott says, just happens to be a word that Ed Fife came up with back in the day. It doesn't necessarily mean anything. I guess he just picked it to represent his product line. So TIFO is the actual product that is utilized. And in this case, for glass, we have what's called a unidirectional product, in that the fibers are running in just two directions. One direction, back and forth in one orientation. So this SEH51A is a glass fiber product. We have a couple other glass material products that come into play. The unidirectional one is the one that's utilized most often, but what we call TIFO web, it's the fibers are oriented 0 and 90 degrees. and then a TIFO BCC, which is what we call a bidirectional material, where the fibers are oriented plus or minus 45 degrees. And then what we have for epoxy, so we're, when we apply this material, we're going to saturate it with epoxy before we apply it to the concrete, apply it to the masonry. And the epoxy that comes into play from the TIFO side is what we call TIFO S. It's a two-part system that's mixed together. Then we have what we call a thickening agent or an inert filler that we add to that epoxy, and that's laid down, and that we, that creates that bonding that the fabric is attached to. The thickened epoxy is also used on the finish as a finish surface for covering up any butted, joints that butt up against each other, corners, edges of fabric, and make sure there's nothing protruding. We have what's called an Sch41 epoxy for underwater applications that's approved for underwater. The main one that's going to come into play most often is our TIFO S. So carbon fiber materials, again, unidirectional, are the ones that come up most often. And from the TIFO side, we have two different products, Sch41 and Sch412x. They're pretty much similar makeup. The main difference is the thickness. So Sch41 is approximately 0.04 inches thick, and 2x is 0.08. And it's gonna, you can, the decision and the idealized, design will come down, on a case-by-case basis, whether to utilize the single thickness material or, depending on how many total layers you need. Maybe one layer of the 2X might be idealized versus 2 layers of the Sch41. It's on a case-by-case basis, but we have both those thicknesses available. I'm not going to talk too much about the other products, but we do have the carbon in the BCC, which is a bidirectional plus or minus 45 degree direction available as well. And again, the similar epoxies that go along with the carbon fabric, similar as they would with the glass fabric, those are the same. So, sorry about that, lost my headpiece. So we have both glass and carbon to choose from. Well, why or when would you use one versus the other? Why do we have both? And, what's the advantage of one versus the other? Well, just on a purely material comparison standpoint, carbon is stiffer than glass. So it has higher stiffness properties than glass. Glass is a little bit cheaper on a material basis. So when we are looking at glass versus carbon on a given project, often we will take into account, the labor that comes into play, because on a given FRP project, how it tends to break down approximately is the overall cost for install of the FRP is around the ballpark of 70% labor and 30% materials. If we take a look at this structure here on the left with exposed exterior columns, we have access, pretty easy access on all 4 sides of the column, and therefore the labor to to wrap this column is fairly straightforward. So perhaps the glass in this case, we can add, and let me back up for a second to add to the difference. What it's also the kind of the key factor that's going to come down to it in evaluating glass versus the carbon is the installed system that gives you the required performance at the lowest install cost, so be it glass versus fiber. And as I mentioned here, this looks like, it's relatively easy to install. So, and the glass being cheaper, we can get those layers, however many are required, up relatively quickly. And that'll help contribute to kind of keeping our labor time down and our overall costs down. Conversely, maybe if we have a situation where maybe the access is kind of tight, I don't know, maybe there's a beam butting up against the column and it's going to be a little trickier to to feed the material through, and you have a certain performance criteria that you're trying to meet. Well, in that case, instead of maybe putting up 2 or 3 layers, taking the labor time to put up 2 or 3 layers of glass, to meet the same performance criteria, it might be decided to just go with 1 layer of carbon, and that might make more sense. So on a microscopic level, if we take a look at a sheet of fabric, that sheet of fabric is composed of what we call bundles of carbon fiber strands. So each given sheet, we sew together these bundles, this photo on the left, or these are called tows. And then if we look at the individual tow on a microscopic level, you see that it's composed of thousands of strands of either glass or carbon. And these materials sewn together and you know, the fabric created, that contributes to the tensile capacity of the material. So the tensile strength, the stiffness of the FRP material. The durability that comes into play in terms of, you know, resisting seismic cycling, you know, withstanding the elements, the durability is affected by the actual composite, or, you know, the fact that we're actually saturating that fabric with epoxy and coming up with our composite. So we talked a little bit about the material and, you know, the difference between glass and fiber, the material makeup. When it comes down to design, so this is a curve, a stress strain curve, and we've got the green curve is representing carbon, and the blue is glass, and the black is grade 60 steel. And what this is showing is the FRP materials, their stress strain behavior is on a linear elastic basis versus steel, where you have some linear elasticity, but after a certain period of time, you are yielding and then you go plastic. So that's the difference here. When we're designing with FRP for any given material that we might be applying it to, be it, you know, a concrete column, a wall, a beam, or masonry, the process involves looking at that individual component, the performance that you're trying to get out of it, and you're designing on a strain compatibility basis. So you're going to match up the properties, the modulus of elasticity of the carbon fiber or glass fiber material with the strain properties of the material, and you're going to design to kind of idealize that and minimize the you know, what do you call it, just be able to take full advantage of the material properties of the FRP. The codes that come into play that are applicable to FRP include ACI 440 in the US. And this is more of a guideline versus a code. We are in the process, people say, well, it would be great if FRP could actually be included and recognized by the code. We have been in the process of moving in that direction. Scott Arnold sits on various committees and, you know, actively looking to, you know, eventually get FRP recognized in the actual building code. But the ACI 440, it does a pretty good job in terms of providing a guideline for engineers in the way of helping come up with the performance criteria, the different parameters that are involved to take into consideration, be it if you're, you know, looking to wrap a column versus, you know, applying to a wall or a slab or a beam and such. Whoops, sorry, I went the wrong way. So what can we do with the FRP material? Well, if we're looking at columns and we're looking to improve the strength of columns, maybe you've got a given column that is vulnerable and deemed to be vulnerable in an earthquake, maybe minimum hoops, minimum lateral reinforcement there. So we can improve on the shear capability. We can improve on displacement. We can, in some, and in most cases, in those two first ones will involve, as you look at this column here on the right, wrapping of the column with the fibers in the horizontal orientation up the height of the column. In some cases, we can contribute to adding flexural strength and orienting fibers vertically up and down the height of the column. And there's a star there that notes that maybe additional considerations may need to take into account, and that would generally be ensuring that you're detailing, you know, at your boundary conditions or your boundary elements, top and bottom, to help ensure that you can actually develop the fibers vertically that are attached to the column. Note at the bottom here that these are what are quote unquote contact critical applications. When we say contact critical, what we're referring to is that as you're wrapping the column with the material is, so you're wrapping it and it actually, you have an overlap. So it actually wraps onto each other at the end about 12 inches past. And what that is known to be is in intimate contact with the base material. And technically speaking, for applications that are contact critical, mostly column wrapping, for a quality control special inspection standpoint, you're not required to do an adhesion test in the field. The alternative, when we're talking about applying to beams and slabs, which I'll talk about in a little while, is that's considered to be a quote unquote bond critical application. And in those cases, we do need to have some verification, some quality control in the field, where we'll be required to do some adhesion testing, in addition to the required daily sample tests, excuse me, samples that are taken and sent to the lab for testing of the material that's actually going up. So when the company first started back in the early 90s, and Ed Fife had the idea of, you know, Caltrans was, you know, doing a lot of steel column jacketing for retrofitting of bridge columns in California. And Ed Fife had the idea of, you know, looking at FRP as a means, as sort of an alternative to consider from a performance basis. And these are some early tests that were done at UCSD. This is a 6-foot diameter column you see on the left there that had gone through testing and some cycling back and forth and experienced some cracks. The decision was made to, you know, install FRP. First of all, the cracks were repaired by epoxy injection. And then FRP material was applied, you know, up and down the length of this column. These are like 2-foot wide strips. And then it was retested. So you see the picture on the right there, it's fully installed, and it was cycled. This is the hysteresis loop from the first test without the installation. And you see that, you know, back and forth cycling on the order of approximately plus or minus 1 inch. And then after that, we start to tail off in terms of its lateral load resistance, its restoring force. It starts to dramatically drop off as far as its load capability laterally. Here we have the hysteresis loops for the FRP installed column superimposed on the uninstalled FRP, and you see, I don't know, is this, let me move this over. Sorry, it might be imposing on the, you see that we're able to achieve displacements on the order of plus or minus 6 inches with no tailing off of the lateral load resistance capacity. In fact, the column did not fail. And it was the limiting factor here was the actual stroke on the machine, which limited out at 6 inches. So quite high performance as an alternative to no FRP. We also did testing of rectangular shaped columns. You see the hysteresis loop on the top there without any FRP, and sort of a displacement limit on the order of 2 inches. And, you know, before you start tailing off in terms of lateral load resistance. We went ahead and proceeded to install the rectangular column with FRP, and again, plus or minus 6 inches with no noticeable loss in lateral load resistance. This one here, as opposed to circular, where, you know, common practice for installing steel jackets, it's a little more challenging to install steel jackets on rectangular shaped columns. So FRP really represents a nice solution where all you got to do, there's minimum preparation before you apply and, you know, put your epoxy down and the fabric. You just need to ensure that you kind of round off the corners a little bit to generate a radius so you don't have too sharp of a corner that might tear the fabric. But other than that, it's pretty straightforward as far as the install goes. And, you know, we get a tremendous gain in performance in the process. Some recent examples of column jacketing applications. On the left-hand side here is a project that is in Palo Alto. It's a historic hotel. It's a, what do you call it? It's on the registry of historic structures. It's a 6-story concrete frame building, and each level the columns were wrapped. We're working with GC plant construction on this. As I mentioned earlier, they we generally have applicators or specialty contractors that we work with that actually install the FRP. But in this case, plant, if you're familiar with plant, they're pretty good sized GC in Northern California. They self-perform concrete, maybe interiors. They decided that they wanted to self-perform FRP on this project. So we went out on site and we trained them. Our field manager and I was in attendance. I got to be on hand for the training, and their crews ended up being very proficient. So, you know, not only wrapping columns, but this project had some unique challenges. If you look at the top of that column where the beam comes in, there's a whole bunch of different conditions. And even just looking at this column where you see we've got a thickness and a ledge here, we got about maybe 5 or 6 inches with this ledge. But just on the other side of this, we have a slightly different condition of the beam where there's actually no ledge. And almost at each column location, there was challenges with different thicknesses of beam, different, you know, conditions, ledges, no ledges. What the design approach was incorporating anchors. It's not shown in this photo. We'll talk about it a little bit later, but installing anchors to create confinement at the column beam intersection. And that was quite a challenge. Plant did a good job on that as well. Their crew was motivated, and they're pretty pleased overall with the process of self-performing the FRP and are looking to continue that. It's not real common that a GC does that, but in this case, there are a few, and they did a good job with it. We have this photo. This is an intake structure that we did a retrofit on recently. And you look down here on the bottom, there's like this is the area where they're preparing their materials. They've got a saturator, which will actually, it's an automated process for applying epoxy to the fabric, and then they will lay it up. This is 8-foot diameter column, and if I'm not mistaken, it's a good 150 feet tall, maybe approaching 200 feet tall. But you see this this installation team down here, relatively low impact for, you know, the exercise that they're doing as far as retrofitting this structure. So we can use FRP to address deficient beams as well, in addition to columns. And one thing I forgot to mention earlier when I started talking about columns and FRP in general is that FRP can be considered as a quote unquote lightweight tension member. And the whole idea when we're designing and looking at FRP, and I'm sure many of you are already aware of this, is that it can, what it can do is actually provide and supplement the ability to replace the steel that ideally you would be able to put in there to achieve the performance criteria that you're looking for on a deficient structure. So it's able to supplement that steel that ideally you wish was there as a lightweight tension member, being the fabric. So when it comes down to beams, we can improve on positive moment, or, you know, supplementing the lower longitudinal bars in this case. Negative moments, the upper bars, shear transfer. So we can, what is it? We can supplement what would be considered to be transverse reinforcement or stirrups if there's a lack there. And then also we can address maybe any need for doing a penetration through the beam for plumbing or whatever. We will then address that on a case-by-case basis, depending on how much reinforcement was cut through in the process, and apply the applicable FRP. Performance of beams. This is a quick slide here that we did some testing and for shear resistance of beams with the strips, the vertically oriented strips, in some cases anchored, and in other cases not. And what we've shown was, you know, applying anchors at the top of these beams with the vertical strip, we were able to improve the shear capacity pretty good compared to no anchors here with the blue mark here at a given displacement. Excuse me. This is a photo example of what we would look like on the left. There is some detailing for a, you know, what looks to be here, maybe like on the order of a 12-inch penetration through this beam. You see the strips on the top and bottom, and then we will wrap, you know, in the near vicinity there to create continuity for the, you know, the both sides of that penetration. This is an example of strengthening of a T-beam or double T. So wall applications, again, when it comes down to FRP, it can be considered as a lightweight tension member. And again, we will be supplementing the ability of, you know, taking the place of reinforcing steel that, you know, you ideally wish you could put in there to improve, you know, the performance for a deficient structure. We can improve on in-plane shear capacity. We can again address cutouts, maybe in a wall, you know, maybe for a door, and then also in-plane flexure and out of plane flexure. So there's a star here for one. I believe, let's see here. Sorry about that. The detailing that we're considering for walls. The additional design considerations. So you see the vertical strip here in addition. So, you know, primarily we'll apply the strips and the horizontal orientation for improving on in-plane shear capacity. And then, you know, if we want to apply some vertical strips here for potential out of plane, we want to make sure that we can, similar to what we were talking about with columns, you know, detail the boundary elements at the top and bottom to ensure we're able to fully develop the fiber. And then for out of plane flexure, you know, in and out of plane, sorry about that, you know, so that would be in plane, I'm thinking about with just one side. But if we're also considering out of plane, often we end up having to not only apply vertical fibers on one side, but likely in most cases we'll want to apply to both sides of that wall. Lastly, we can actually improve or, you know, contribute to shear transfer between two respective wall panels. So what we've done testing where we've used FRP materials to actually stitch together two respective precast panels, and sort of as an alternative to maybe otherwise having to use steel plates and bolts or whatever. So this is a process that we've been testing on and actually had some pretty good success with. Again, here, I don't know if I actually remembered to mention it with beams, but with beams and walls, it's going to involve, so this is we're laying up the material, we're not fully wrapping per se, and so that's what we consider to be a bond critical application. And therefore, in the case of this wall here, in the actual project, we might locate somewhere that's in the nearby vicinity that we select, and we'll install some fabric, and we'll dedicate that location for doing some adhesion testing. So we'll show you how that actually works physically speaking, but basically you put the material down, and then you drill out, so you use a hole saw, and then you install this, like, I don't know, it's like a 3-inch diameter, 4-inch diameter, quote unquote puck, and then you pull. And the idea is that you're actually pulling away the base material, or getting the base material to fracture away, and you're not, you're ensuring that the attached fiber to the material is not, separating from the concrete or the base material for that matter. So here's a photo which shows how we can detail, for a wall opening. And in this case, it incorporates anchors at the header. This is an example of a wall strengthening. This is at the Presidio in San Francisco, where vertical strips were utilized on URM walls. And in this case, sometimes we will utilize anchors on walls like here. And in this case, instead of FRP anchors, they utilize a steel plate at the base. And the idea was to allow for in-plane flexural capacity and minimize the potential for the rocking effect, sort of on more of a rigid basis, and introduce some in-plane flexural ductility capacity and get away from the potential for rocking. So the restraining at the base of the steel plates here work quite well in this case for these tall walls. URM walls, we have some videos that we've done on testing. So what we have is a test that was done where we applied glass fiber strips on one side of a URM wall, anchored at the base, and just on one side, and then we tested it side by side in comparison to an unreinforced wall. And this is just on one side, glass fabric. So for, kind of minimum effort on addressing this structure, we are able to achieve a life safety performance in this case, versus complete collapse with, for a given lateral loading. Excuse me, sorry. We've also done some work on blast hardening or blast effects on walls. This is an example of a masonry wall where they installed FRP on the complete wall, and then in comparison subjected it to some blast relative to no FRP at all. This goes by pretty quick. If we look on the left-hand side, you can see how it is responding versus the right. But holds up pretty well in terms of containment. Structural applications for slabs, not to sort of, kind of repeat myself too much, but again, we're going to be taking advantage of the fact that the FRP material is a lightweight tension member, and it's going to be used to supplement or be able to supplement reinforcing steel that you would like to be able to ideally put into place. Again, addressing or helping improve performance in the way of positive moment or supplementing the ability of installing lower longitudinal bars, negative moment upper longitudinal bars. Cut steel, so penetrations, we can address that. We're we quite a bit of experience right now. We're working on a project in San Francisco. I wish I had some photos, but they have like at one maritime plaza some 6-inch diameter cores through the slab, and they are applying strips of FRP in the vicinity of those cores, the top and bottom of the slabs, for addressing the steel that was cut in the process. Shear transfer. So similar to the vertically oriented walls on slabs, if we've got some precast floor sections, we can transfer between those by stitching them together and creating continuity and minimizing the potential for differential movement of those panels. Punching shear. On the FRP side, we generally defer, if at all possible, to recommending that the slab be thickened. It tends to, from the cost standpoint, addressing punching shear make more sense versus trying to incorporate FRP. A couple of photos of different applications for top of slab. This is an example of the detailing for penetrations, and we've got plumbing coming up through some cores, and then we will accordingly place the strips there to address the loss in capacity based on the reinforcement that was there. Okay, so I'm going to talk a little bit about the process involved for when we have a bond critical application, be it applying to a wall, a beam, a slab, and what comes into play here. So first of all, we have the surface preparation. We've got a primer we're applying, and then we have our thickened epoxy that we put down before we lay down our fabric. We'll let's see here. Okay, surface preparation, first of all, is that we want to either generally we'll apply grinding. We want to remove the latents and expose the aggregate, and generally speaking, that will involve coming down to or achieving what we call a CSP2 surface finish, surface profile. You can, in some cases, go a little bit farther and expose more aggregate, have a more of a finer finish down to CSP3, but generally speaking, a minimum of CSP2 is sufficient and required for bond critical applications. This is the process of, this is what we sort of automated means for coating the fabric with epoxy in the maybe on a smaller scale basis. On a small project, you may just hand apply epoxy to the fabric, but on a decent sized project, we have a saturator involved, and we train the installer on the use of the saturator, and we'll show you here how he's applying the epoxy to the fabric, and then they're actually taking it and putting it up on the structure. So the vat where they're pouring their mixed epoxy. Should add here that it's a two-part epoxy, and that actually gets the fabric is saturated with. once the two parts are mixed, the VOCs that are transmitted are really minimal, and therefore you're actually, and the smell is it's not harmful. Really, it's very minimal, so they can work in tight confined spaces without the need for a mask. Same goes with the thickened agent that is added to that epoxy. Low VOC, and so low impact. You're able to work in tight spaces with, zero or minimal harmful VOC effects. So he's got his roll. He's laying it out here, and they're butting the two rolls, sort of the about 2 foot wide fabric material, fairly close to each other as they're working their way through this tunnel. You see on the right hand side here, this sort of a whitish colored material. That's the what we consider to be our thickened epoxy. So we mix the two parts of the Typho S, and then we add a quote unquote inert filler there of what the and then they'll go back over this with a finish coat of this similar white material to kind of address the butt joints there and seal it off, seal off the fabric to create a finish. This is a similar well, it's a similar process, but it's sealing, building sealing. He's going through with the thickened epoxy and covering up the edges, covering up the material, creating a finish effect there. Whoops. So we're going to talk a little bit about anchors. So glass fiber anchors, carbon fiber anchors, these can be used to supplement the fabric in some cases where we need to maybe transfer load into the concrete, or create continuity, confinement. They come into play and can work out to be quite handy in some cases. The slide on the left, or the graphic on the left there, shows a wall, and on the left hand side, if you look at the cut section, you can see that we have the ability of wrapping the material around the corner. But on the right, there might be some obstruction there, or like maybe another wall framing in or something where you don't have access to the back side of this wall. And therefore, we would maybe embed, drill holes, embed into the, maybe the corner there, and then, install these anchors, and then fan out the other end there. And then what we'll do is we generally apply another roll of fabric over the top of this fan here to create a sandwich. Similarly, here we have a column, maybe we're a wall, and you don't have access all the way around this column to be able to wrap, as we were showing earlier. So we might want to consider utilizing anchors here to embed a certain distance, and then we would fan out that anchor on the surface of the column. This is for the retrofit of the beam. Let's see if I can minimize this. It looks like I'm where I can put this thing. Sorry about that. Having a hard time getting rid of this. You see the anchor is coming down here, fanning across, and then they come back with another layer of fabric to create the sandwich effect for the anchors. So we're enhancing the shear capacity of this beam and using anchors to help do that. What's going on with my controls here? Sorry about that. Okay, a couple other details. We can utilize anchors here where we have an intersection or an interruption. So we're trying to go through a wall here or a beam, and to create the continuity and to develop the fabric from the beam and this obstruction and continue past this beam. Here is a close-up look of what the anchors look like before they're saturated. So they come and we saturate them with epoxy before we install them. This is how they come, and then we fan out the ends, or in some cases we'll install the one end into the concrete and then fan out the other, or in some cases we'll fan out both sides when we have like a through anchor situation. I'm going to try to move along here because I'm getting close to the time, but I have a few slides, but for some reason, the slide advance is not working. Sorry about that. What is going on? Okay. Okay, this is another example. So we're utilizing anchors, in this case on a through anchor basis, for confinement at the column beam intersection. So I spoke a little bit about this. This is the current project in Palo Alto. It's a historic hotel, which we're working with plant construction. And a variety of, over the course of the 6 levels, a variety of different conditions at where the beams frame into the column. The challenge was to, address these with the right size anchor for getting the desired confinement. Along with that is that, the existing reinforcing steel. So this is a through hole that was drilled through here. Okay, and we run the anchor through, and then we fan it out on the face of the beam on both sides. First, you put down a piece of fabric, you install your anchor, and then you will sandwich that with another piece of fabric. But this is a pretty unique situation in that there was a variety of different conditions. So there was almost not a single location from one column to the next where you had, similar. So it was a challenge. We had about, I don't know, a good 5 or 6 different anchor designs utilizing, depending on how much height you had to work with here of your beam, depending on whether or not there was a ledge, different diameters that were incorporated, or whether you would just utilize one anchor versus 2. But Plant did a really great job as far as communicating conditions in the field and actually executing the install of the anchors. They were not deterred, but this is a pretty cool one as far as what the anchors can do in the way of creating that confinement at the column beam intersection. Oh, come on, please. Lastly, we have a condition where we can utilize anchors where we have a wall obstruction. We've got these the material on the slab that we're reinforcing, and we want to we come across this, so we can utilize anchors to run those through, fan out on both sides, and be able to develop our material for our slab reinforcement. Okay, a few last slides here. Surface preparation and finish. Not something that engineers maybe always think about for FRP, but ends up being quite important. And what we try to make sure that folks are aware of in the design process, or that ends up in the construction documents. First of all, consideration the material itself, whether what's going to be the finish, or what's the end use. Are people going to be able to come up and touch it? Is it going to be hidden, where it doesn't really matter? Is just a say, for instance, the thickened epoxy, is that sufficient? Or do you want to be able to, paint it and kind of match with the existing? We've done lots of different finishes over the years. And, if people are, going to be needing to come up or get close to it and touch it, it's important that it looks good and maybe try to match as much as possible with the surrounding area. This is one example of a type of finish. So for a elevated train column here, what we have, what's called a typo RR. It's a what we call an intermediate coat. It's actually a class 1 flame and smoke fire retardant. It has some fire resistant capabilities. Mostly it can be used in conjunction with installing over our thickened epoxy coat and sort of as an intermediate coat, in that it bonds really well to the thickened epoxy and allows for putting a finished paint on to match, again, the surrounding. But you have it's like a little bit like a stucco-like texture, but it's a pretty common one that we utilize as a intermediate coat, and kind of works pretty well as a durable finish. Fire protection considerations. We do have, so for the underside of the slab, in case where you have a gravity load condition versus seismic, fire protection needs to be considered. We do have fire protection coatings that are different rated, and certainly we can help you with that. I'm not going to go into too much detail here because we're running short on time. This is just a quick example where we have an underside of a slab and applying FRP and then coming back with 4-hour rated spraying on fire protection. Okay, lastly, I touched on it at the beginning, but we offer certification and training for installers, and it's pretty thorough. It's a 2-day training, and any decent sized project is going to use a saturator, so an automated means for soaking that material, and we'll train them on the use of that. We also train on and this is a requirement for most projects, in that as you're installing material, you are required to create samples, 12 by 12 sheets. Maybe some of you have seen these if you've been involved on an FRP project, but you create a laminate similar to the laminate that you're applying to the wall, to the slab, and you usually at least required to do 2 per day, if not 4. Those are prepared and they are submitted to the lab. The lab then takes that 12 by 12 sample and they cut it into vertical strips, 5 vertical strips, which they have put into I'm going to kind of move quickly here. They test it for tension. So these prepared squares are field tested. This is I talked a little bit about it, but this is a photo example of that adhesion test that I was mentioning. We have like a dedicated area here that's away from the actual production. They might actually come back and go over this with production material, but they designate this for their field testing, and they pull these pucks where the base material is required to fail. I won't worry about that. Last thing. If indeed that you are looking to consider FRP and wondering if it might be an option, you want some feedback, one of the things we ask is that we have that we can provide you with is a design questionnaire, which kind of helps sort of cover some of the parameters that we look for and helping you to come up with your performance criteria and whether or not it's going to be feasible, based on your existing conditions, what you're looking for a finish, and so we can help guide you there. And of course, we can always just field questions from an email and phone call as well too. But the design questionnaire does kind of formalize it a little bit and help sort of get the details on paper. That's all I have. I'm sorry I kind of ran a little bit over, and happy to get with any questions, maybe for the purposes of time, if folks maybe want to email me stuff. If they have any questions, I didn't even check the chat here. Let's see.
Yeah, I think Sean had one question in the chat I saw. But
Okay, the CMU grouted, or yeah, the cells, was it fully grouted or partially grouted? I think it was ungrouted, if I'm not mistaken. See, has Fife done similar tests with brick? So we've done it. I'm not sure about exactly testing. I know we've done a couple projects to date applying FRP to URM. Certainly can get with you and provide some examples on applications.
we did, well, I don't know if it was URM, but it was very reduced reinforced masonry in San Diego with use.
Okay. Like
Um,
partially grouted block or something like that, or like,
no, it was brick, but it was very lightly reinforced.
oh, okay.
Added a
Okay.
story to a building, and you know, Wayne in San Diego was pretty up to date on what we did there. It turned out pretty well, actually. It was probably the best solution by far. We had those anchors and
low impact.
Yeah.
Okay,
yeah.
Good, great.
Good project. So,
well, I appreciate everyone's time and the opportunity today. Sorry,
Marty, I have a question. I'm sorry, before
yes.
you leave, I have a quick question. Do you guys provide the engineering service also? If I want to design a column or something, use FRP, do you guys provide the composite section properties? How do I use your?
Yeah, so we can, so based on, you know, your existing conditions, and, you know, you have an idea of performance that you're looking to try to get out of that, you know, based on anticipated loading that it's subject to, we will help with you to provide an FRP design to address the performance criteria that you're looking for, free of charge.
So you provide the section properties, actually?
Yes. Yes,
okay.
We'll provide you the required, you know, width, the number of layers, the particular material, would be it glass or carbon fiber, you know, for the given project.
Sounds good. And one more question: do you guys did any experiment for the FRP or glass the glass wrap with the wood?
With the what? I'm sorry.
With wood.
Wood.
Timber.
Wood.
Timber.
Oh, wood. You know what? I think on a limited basis, it's mostly concrete and masonry, some steel. It's been looked at. There may have been. I can look into that. I can look and see what we have. I think there may have been a little bit to date. Yeah.
All right. Thank you so much.
Sure. Your name was, is it Hamid?
Hamid, yes.
Okay. I will check on that and see what I can find out.
Awesome. Thank you. Thank you.
Okay. Sure.
all right. Well, I think we've run over a little bit, but some good questions. Marty, thanks for the presentation. I really appreciate you going company-wide. I think you were, I didn't see everybody that was on, but we had people from Italy, Haiti,
Oh, wow.
New Zealand, the US, and, you know, maybe other places. So
Nice.
I'm glad we expanded this out of just one office. So thank you everyone for showing up and paying attention. A really good presentation. So,
Thanks for your help, Jeff, getting this set up. Appreciate it. And Letitia, I don't know if she's on, but I appreciate all her help coordinating with me to set up a date. Yeah.
all right.
Terrific. All right. And yeah, happy to get with anybody on any follow-up questions, or if we can be assistance for a project, you know, considering FRP down the line.
Yeah. Thank you.
All right. Have a good rest of your day.
All right. Good deal. Thanks.
Take care.
Bye-bye,
Bye-bye.
everyone.